Good morning to the class. In this lecture, Water Reticulation 3A, we continue with the section on stormwater design. And in the last lecture, I mentioned to you that I'll go through the worked example in the Itegbini design manual. Before we proceed, I just want to check, do you see the PDF file on your screen? One of you could please confirm. Anybody? One of you could maybe just mute your mic or show a thumbs up or something. Can you see the PDF file on your screen?
Yes, sir.
Okay, thank you for that. Thanks for that. Okay, the example you're seeing, this is in the Itegbini design manual, and I just want to go through it. And I also have an alternate working for you where some of the calcs may be a little simpler, just for the first two catchment areas. And I'll show that to you also at the end of this lecture. And, in this design worked example, you see uh, we have four catchment areas. Uh, Now, these catchment areas for the design of this, you would pick this up from a map or a survey that you may have been given, and you would pick up these catchment areas from the. You don't really have the choice to decide the boundaries of the catchment area. That you would pick it up from an orthographic map or a contour map. You would look for the ridge points, the high points. If you look carefully on this drawing, you'll see here the solid line is a ridge line over here. You'll notice here, it does actually tell you that there's a ridge line over there. So this information, you would pick it up from maps, and you would need the ability to read maps and be able to pick up that, or even from a contour drawing where you'd look for the high contours, and then when you start seeing the contours number lowering again, then you know you're at a ridge line, and you would pick up the ridge lines at that. So that's how you would go about identifying your catchment areas like this over here. Right, so that's what's picked up as. Initially, when students are engaged in designing office, if you are, for example, this developing, and I'm just using an example. If you would maybe have developed just that area there, for example, like that, if you have just what I've shown in blue, if you are concentrated in that area and you now have to design the stormwater reticulation for this area, it would be a common error where students would use this blue line as the catchment area, right? Forgetting that actually the stormwater from the rest of the catchment would still flow through your development through this blue line. So any stormwater that falls, for example, down there, is going to find its way down and pass through your developed area like that. So it's important for you to identify the ridge lines or the highest points, and once you've done that, you can then mark up your actual catchment areas. And I'll stress that you don't have a discretion in terms of deciding these catchments, right? The extent of it or the size of the catchment area. And that's how it is in nature when you go out there. So, for example, there might be a hill here, and that divides any rainfall flowing on this hill. Some of it's either going to flow down the hill on the left hand side down like that, or on the right hand side down like. So that will be your watershed, what we would refer to as a watershed, if you've done geography in school or you've done geology at campus. Right? So you would go about in a map and identify these catchment areas, and that's what's been done over here. So we have four catchment areas. Once you've determined the catchment area, you then determine the type of flow that you're going to get. So you would know the high points. Obviously, the high points would be near the ridge areas, and it would be the water would drain. And you then need to look at whether you have any natural water causes, or whether you're going to have overland flow. Now, in this particular example, it's overland flow, even though it's not explicitly stated. If you're designing a stormwater reticulation, in all likelihood, you would have probably seen the area, or maybe you would have walked through it and visited the area to determine the kind of vegetation and the slope of the ground and the features that are there. Or you might even have looked at in today's times, it's quite easy. You can look at Google Maps and pick up, just looking at it, and you pick up information from there. Right, so in this particular exercise here, we're looking at overland flow because there is no natural water course that has formed in these catchments over here. So we have these four catchment areas. Now, the stormwater reticulation that's being designed, you'll notice that there's a curb or there's a inlet, a culvert inlet at point A. So there's an inlet point, and then the stormwater is piped down from A to B. Right. So obviously we're going to have to size that pipe AB. We'll have to determine a size for that pipe AB. And then at point B, there's again another inlet and also a bin. So that's like a catch pit manhole kind of scenario at B. And we have the in small, and let me enlarge that. You'll see the B1 or B prime. I think it's B1 there. That's called that B1 is a catch pit that picks up the flow from catchment area 2, and then that's piped into that B1, and then from B, so it's piped into from B1 to B, and from B to C, we then have a second pipe flow for that. So we would then need to determine the flow in B to C1 over there. Now, the flow from B to C1 would be the flow that arrives from catchment area A and catchment area from the catchment area 1 and catchment area 2. From C1, it flows to C2, and you then see catchment area 3. The flow from that then flows into C2, and then again from C2, it's piped from C2 to D, and then from D to E, and then from E to F, where you have again an outlet chamber. And it's then outlet into what looks like the natural water course or a stream or something down there at the bottom. That's looking again at also at this design. If you've been through the manual or you've perused it, you'll identify what's referred to as, or you need to identify what's referred to as critical points. When you're designing stormwater, then you need to identify the critical points. And these critical points are defined in the notes for you. I'll go there to that point just now and tell you. And one of them is a low point like this, because at a critical point, if you get flooding, then you might get extensive damage. There might be valuable property or maybe damage to a road if you get erosion, overflow, or something like that. In this particular one, it looks like you might get overflow over the road, and you might get some erosion and might be washed away at that point. Now, why do you need to identify these critical points? In the Iteguini design manual, they mention that. It's because the stormwater event that you design for, that you need to know what kind of event you're designing for. The first thing is this is not a huge regional design. Uh, for example, it's not the stormwater for Iteguini municipality themselves, their main, considering their main stormwater channels and things like that. This is a minor system. Looking at this, you can pick it up from the area, the drainage area that you're designing. 2 hectares, you're given the area of each of these catchment areas. 2 hectares, 1 hectare is 10,000 square meters. So that's not an extensively large area. It's like a normal suburb or something that you're designing. So it's a minor system that you're designing. So that's the first thing to identify. You're designing a major one, or you're designing a minor stormwater system. So you're designing a minor stormwater system. For the minor stormwater system, you might be designing for a 1 in 3 return period or 1 in 5 return period. But when you have critical points, like the low point at C, that you've identified as critical points, your design needs to be for a 1 in 10 year storm, right, to prevent damage or loss to property or loss to life or damage, extensive damage to infrastructure. Right? So, so it means that from the C2 downwards, we will design it for a 1 in 10 year return period, and above C2, for example, from A to B, we can design that for a 1 in 3 year return period. Right? So going to the example, there is some discussion about that. You're also given the lengths for from the furthest point in the catchment to the point of concern. So we want to first measure the amount of water that arrives at point A. That will be the first part of the design. Um, just as a side note, when you're designing stormwater, you will always design from the upstream portion and then move downstream. It's fairly obvious, it's a natural thing to do. Because as you move downstream, you will need the flows that are arriving at the upstream points, right? So you cannot determine the flow at the downstream point without knowing what flow you have at the upstream point. So you cannot start off, for example, and say, I'm going to design now pipeline DE, because to design pipeline DE, you would need to know what's the flow in that pipe. And to get that flow, you would need to know what's the flow in pipeline AB, because whatever is flowing in pipeline AB is also passing through that pipeline DE. Right, so we will start off at the most upstream point. So you start off at the point A. First, you need to work out how much of flow arrives at point A. To do that, that's what's done in the first step of the calculations. You'll see that down here. So this to say consider point of entry at A in this set of notes here. That's what they're saying. Consider the point of entry at A, and to determine that, you're going to use the rational formula. For the rational formula, you know that you will need the catchment area, and it's measured in hectares. So it's 2 hectares that you have there, or 20,000 square meters. But the formula that you have that's given in this particular book here that I mentioned to you, that was that's in hectares, that formula. Right, so that's sorted out. You know the area. Um, then, okay, let me just go back. You're going to need the rainfall intensity, and you're going to need a runoff coefficient from the rational formula. Let's just go back and let me just find the rational formula for you. Just have a look at that, and then you'll see from there what information you're going to need. Sorry, just bear with me. Well, that's a little further up, slow. Getting closer. Right, that's the rational formula that you have there, right? So uh, to use this rational formula, you'll recall from the last time, FT is the return period. That's about 2 pages beneath this. So as we're passing by, we'll just note the factor for the return period. And the runoff coefficient, that we'll have to use the table to determine the runoff coefficient and the rainfall intensity and the area. Right. So these are the variables. We already know what the A is over here, and you'll notice in this formula here that the A is measured in hectares. So we now the rest of our efforts will concentrate around the remaining 3 variables over here. Right. So let's see. First, the easiest one to look up is that your return period. That's just further down in the set of notes that you'll find here. That's the return period, the stormwater return period. Now, the set of notes that we have here, it was initially written, it's done by Itigwini themselves, and it was written for a 1 in 5 year return period. And I think after further to that, they later changed a minor stormwater design to a 3 year event. So everything that's calculated is calculated for a 5 year event, and they do have a note in the solution over there. So they're working with a 1 in 5 year, so that's where the FT of 0.55. So we now know what the reduction factor for that 1 in 5 year return period is 0.55. They don't have a value for 1 in 3 years, so you would have to interpolate between these two values. Right? If you want to actually correct the design that they have produced over here in this calculation. But we'll continue because the example is based on a 1 in 5 year. So we'll continue with using that value there. So having done that, we can then proceed. We then need we then have to decide. So I just want to go back. I think it was page 27. Yes. We then need the C value and the I value. So we will then proceed towards that. For the runoff coefficient value, I'll do that first, and then I'll come to the I value, and then all our effort after that will be based on that I value. The runoff coefficient, you'll see they've just given the calculation here, and the first question that's going to come to your mind as students is, well, where do all of these values come from? You don't know any information about anything over here. Okay, so the first one you see is the CS is the slope coefficient, CP is the permeability, and CR, that's from the table, the last value, that's okay, the soil, the permeability, and then the third one, okay, I'll just check it up on the table. I'll tell you now what the third one is for. Just got a slip of memory. The third one is for your vegetation growth, right? The well, yeah, the kind of vegetation that you have in that area there. So let's look at and then this will give us our rural catchment area, right? The runoff coefficient for the rural area. Now, for the first one, for this the catchment slope factor, we need information about that. We can determine what the catchment slope is. We know from the furthest point to the point of consideration A, we have 150 meters, and we need information about what's the fall from that point over there. What's the fall? And there is that you are given information about that. The height of fall that occurs in that area. There's a 4 meter difference in that fall. From where you're starting off over there. So that's a 4 meter. And then based on that, you can then determine the slope of the ground over there. Right. So uh, now in practice, so how would you determine that fall or what's the fall? You would have to look up the contour map or something, or you'd need survey information or something like that. You cannot just guess the fall just looking at it. Like so, you would need information. That information would be provided for you. Right. It's not explicitly given in this particular figure here. When you look at it like that, you're just given the length of the catchments, but the actual fall that's given to you in these solutions. So, but that's something you cannot just know like that. You would have to be provided information. So, for you in a test or exam situation, you would be provided with what the fall is, or you will be shown contours on the drawings, and you would then determine it from the contours layout. Right? So, once you've got the length and that fall, from that you can work out what's the average slope for that area. And also you need to know whether you got whether it's a defined water course or whether you got overland flow. Right, so we're looking at for the 4 divided by 150, that gives you that's about a 3% slope, right? In that catchment area A. That's the slope for that catchment area. So that would determine the C value over here because you need that slope value to determine what coefficient you're going to use here. So let's go back to the table, and that's so I'm just going to go up. It's 3 or 4 pages up here, and let's just look at that for this particular. This is the table in concern that we have here. So the first one was that value for CS. That's the slope coefficient. And we see that for less than 3%, we have a value of 0.05. Right? 0.05, and that's the value that's being used in this particular calculation over here, 0.05. Right? Less than or equal to 3% would be around that value. And it's 3%. If you look at if you work out that value 4 divided by 150, so take out my calculator and just double check that. So that's 4 divided by 150. You can also double check that and see it's actually 0.0227. So it's slightly less than 3%. If you multiply that by 100, if I multiply it, the exact percentage is 2.7%, but it's been rounded to 3% in those calculations. Right? So that's why the 0.05 is being used. It's actually slightly less than 3%. If it was 3% or more, then you'd have used the 0.11. Now, for the catchment, that's the entire catchment is based on that slope over there. So in this particular one that you're seeing on the screen, this table, that was 20%. So in our case, this value here, this 20 would be 100%, and the rest of those values would be zero. So that's why we would get a value, final value of 0.05 for the slope over here. Right, but if you knew differently about the slope, if portions of it were sloped differently, we don't have any information other than that, so we cannot try and spread it out over these different slopes. So we take all of it, 100% of it is less than 3%, and we get a value of 0.11 for that 100% of the catchment area A. Right. Then the permeability of that catchment area A, again, you now need to make a decision on that. Now, unless you may have some geotechnical information or first-hand experience about the soils. But if you, as a design engineer, if you have this maybe walked the site or visited it, you would have some idea from the terrain, looking at the kind of terrain there, more or less what would the soil permeability be. And you see, it says here for most soils, it is a soil permeability of 0.2, right? For most soils, they would generally that would be a coefficient that you would use 0.2 for most soils. So without being given any other information here, that's what we would assume. That's 0.02. You can look at maybe a Google map and have a look at that area to see if there's any rock or paving or something, or the dunes. Dunes would be closer to the coast. If you are right on the beach or something, you may have dunes there. Uh, Light soil, again, that would be a very permeable soil or most soils. So we will opt for most soils. And again, we're assuming the entire catchment area to be this of this one uh, type of soil uniform. So that's why we're going to substitute 100% here in this table for at this point, and the other values will be zero. The other yellow values will be zero, and we'll end up with a coefficient of 0.2. And that's what was done in this particular example. Same for vegetable growth. Again, in the Durban area, it's unlikely you're going to be doing a development in dense bush or forest. So uh, most of the land in Durban would generally fall under grassland. At the bare surface is usually a desert area. So we're not in that kind of, or maybe along the beach, the sand in the beach. Uh, Cultivated land, it's not farmed. Cultivated land means it's a farmed area. So the natural thing, without being provided any further information about that area, you may look at Google Maps for those coordinates and look at it, and we would assume it's a grassland area. So that's why we're getting a value of 0.25. And again, we're putting 100 at that point. The entire catchment we're assuming is grassland. So the rest of those values would be zero. Right. So in this table, this is how we would populate it, or that's what's being done in this particular example. The same thing for the permeability. If I may just fill there, that would be 100, and the other values we're taking it as zero. So the weighted factor or the actual final factor that we would get if you add all of those values, you see that will be zero point 0.2. We get zero point 0.2. This one over here, we would get zero point 0.2, sorry, 0.25 there, not 0.25 for that one. And then the first one, similarly, you pick up here a 0.05 for this one. And again, you'll amend the yellow ones like that. So that's what was done for that particular one. Let me go back to that calculations, and you'll see these values. So it's not explicitly explained in the solution how these values were arrived at. So that's why I'm explaining it to you, where you see these values 0.05, 0.2, and 0.25 over here. Right. So once you've got these values, you can then work out your runoff coefficients. You just add these values up, and that's what gave this runoff coefficient of 0.05 over here. So once that's done, so we now have three of the four variables that we've calculated for our rational formula. So we now need to concentrate our efforts on determining the intensity, right, of the rainfall that we need for the rational method. Now, this is the note I mentioned about the 1 in 3 year storm, but everything here is done for the calcs are done for the 1 in 5 years, the return period. So that's why that particular 0.55 was used for the return period, the value over there. Right, and I mentioned too that for 3 year you can interpolate between those values of that. Uh, Now, to determine the rainfall intensity, the first is we need what's the point rainfall at that particular point. So for this particular site, this would have been on a map or a survey. You'd have the X and Y coordinates for this area. To design it, to do the stormwater design, you would need that information. You need, if it's in the eThekwini, you need to know what's the latitude, what's the longitude for this area. That information, you might pick it up from an orthographic map, from Google Maps, you could pick it up, or from the surveyor. The surveyor might give you that information. So that is provided for you in this particular example. The site latitude and the site longitude is given to you. So you can see the latitude 2944 and the longitude 3050. Right. So maybe just make a note of that of those two values. Because I'm going to have to unshare the screen and I'll go to Excel and I'll show you how we find the rainfall intensity for this particular place over here. Right. And uh, the interpolation for you is done. And you'll get a value here for, I mean, okay, this okay, 98.5 over there. That's the value. But where did this value come from? Uh, sorry, not 98.5. Uh, you're just given the final intensity in terms of 99 millimeters per hour. To do that, you need the point rainfall and you need the concentration time also to determine that value before you can substitute in this particular formula. Right. So I'll come back to the concentration. Okay, sorry. Before we can determine the point rainfall, we're going to need the concentration time to substitute to determine the point rainfall. The point rainfall it depends also on the concentration time or the duration of the storm, put it that way. Right? So for this particular catchment area that we have, area A, the concentration time would be the time it would take water from the furthest point to arrive at our point of consideration. At the moment, we're considering the inlet at A. So how long would it take water from the furthest point in the catchment to arrive at that point? We're assuming overland flow in this particular calculation because there is no defined water course. The defined water course you can see is at the bottom there. So at this point, we're assuming that it's overland flow. So we'll use the Kirby formula and in the Kirby formula, to substitute for that, we have to determine that's, so let me just erase the blue line. So to determine the Kirby formula is given to you at this point. It's given in the notes. It's explained to you. Uh, the S is the slope. Right? The L is the length of it. The length is given to you, and the R that's a coefficient depending on the slope and various other factors that you would need to determine for this Kirby formula. Right, so we'll go back and look at and determine what R or how the R is determined for this. In this particular calculation, what value of R was used here. And then we just substitute those values in this, and then we'll get the concentration time. Looking at this, the slope was 3%. So that's the assumption that's made here. Slope 3, not assumption. We determined that 3% from that point over there. The length is 150. That's given to you in this particular drawing here. So you would have scaled it off or measured it with your ruler or something and determined the 150 there. And then the last value is that R value, the runoff coefficient, that R value. And that has come from a table where you have that Kirby formula. And when you substitute into that formula, you get a concentration time of 22.5 minutes. Now let's go back and look at that Kirby formula. Just bear with me. I'll just find the just looking for that particular formula. That's the formula that we have here, the Kirby formula. You see the Kirby formula. And the runoff coefficients are given over here. And again, remember for this, we made an assumption of moderate grassland. So for that particular one, you see you have here 0 0.4, the R factor, the runoff factor, for or the roughness factor. So that's what it's called, the roughness factor or the runoff factor for this Kirby formula. So that's where it's come from. When we used the overall, when we used determine the coefficient, the runoff coefficient also, we assumed moderate grass there. So it's consistent with that. And that you get zero point 0.4 at that point over there. Remember, we used the grassland, right? So grassland. So that would be consistent with moderate grass over there. That's where that has come from. So you can see quite a few assumptions needed to be made. And if you substitute in that formula, you get the value of 22.5 minutes. Now, once you've got the 22.5 minutes, that means it takes at least 22.5 minutes for all the runoff in this catchment area, whatever runoff is, it would take for that runoff to reach point A. The rain may start, for example, any runoff that fell at that point may reach point A within maybe 5 minutes or 3 minutes or 2 minutes. But if you want the most intense flow, for the most intense flow would mean that all the runoff that's arriving at A must arrive at the same time at a one particular moment. You're getting runoff from all portions of your catchment. So if you took, for example, a 5 minute period, then the runoff at this point in 5 minutes time would be at point A, but the runoff from that point would not have reached at A as yet. That runoff might still be sitting somewhere down at that point over there. Right. So what arrived at A would be gone down the pipe and gone. And the one that's from this furthest point is still actually hasn't even, is nowhere near point A. It would arrive much later, 15 minutes later when it would arrive and flow down the pipe. So if you want the largest flow in the pipe, you want runoff from all regions in your catchment area to be reaching point A. And that will only happen after 20, if the storm if it was raining consistently for 22 minutes or 23 minutes. So once it starts raining, once you got a rainfall that's the intensity that's lasting for that duration, let's say 23 minutes, then whatever rainfall is falling at A is arriving at point A, and even the rainfall that's at the furthest point is also at point A. So now you have flow from the entire catchment that's actually reaching point A at that moment in time, at the 23-minute in time, there's flow, or even whether it's 24 minutes or 26 minutes or from any period longer than that, it means that rainfall from every part of this catchment is now arriving at point A and would be flowing through that pipe. So that would be the most intense flow that you would get in that pipeline AB. And so that's our concentration time, 22.5 minutes. We now, okay, just bear with me. I'm now going to work out the intensity. Uh, Intensity is millimeter per hour. So we got the per hour part. You can convert the 22.5 into hours, but the millimeter part, the point rainfall, right? We need that. How many millimeters of rain uh, can fall in a 22.5 minute time period. How many millimeter point rainfall can fall at any point in this catchment area? So to determine that, right, we need the coordinates, and that's the coordinates that's given. And I told you just make a note of that, right? So 29 degree, 44 minutes, and 30 degree, 50 minutes, the longitude, that latitude and longitude. Now, we will then need to go to the eThekwini website and download the spreadsheet. I've downloaded it for you. It's on Moodle. You can download it from there. Just bear with me. I'm going to unshare my file, and I'm now going to share with you uh, the Excel file for that. Right. So, uh, if I may confirm, do you see the Excel spreadsheet on your screen now? One of you could please just confirm. Do you see the Excel spreadsheet?
Yes.
Okay,
Yes.
right. Okay, so you see the Excel spreadsheet. Note that when we look at the legend here that's given, we got the return period. So that's these calcs are being done for a 1 in 5 year storm, right? So the RP value, the return period must be 1 in 5 years. Although now the more later updated version says you must design it for a 1 in 3 year storm if you're doing a minor stormwater design. And then the design rainfall for the event duration. Now they got for 15 minutes and for 30 minutes. They don't have for 22.5 minutes. So we're going to interpolate. We'll have to read off those two values, M15 and M30, read off those two values and interpolate from those two values. Right? So that's what we'll be looking at, those particular columns, M15 and M30. Right? So when you look at the bottom here, the tabs at the bottom of the screen, you'll see the first one is 2929. That's not what we want. We're looking for 2944. So that's what we will have to look for. So you need to page down and just go at the bottom there, 29. I want to just carry on. Okay, now I need to, sorry, just bear with me. How do I make this that? You can see the, I'm not adding more, 2944. Okay. You can see I found the 2944 at the bottom here. Right, so that's the 2944. So that's the worksheet I've got. So that's the latitude, 2944. Right, so you can see 2944. And now I need to go across, or I need to look at the longitude. If you look at the, and go back here on the top, you see here, right, so latitude 29, all the first two columns are all 2944 because that's what this particular tab is. It's all for 2944. The longitude then says, I'm looking for 30 degrees and 50 minutes. So 30 degrees, 30 minutes, 30 degrees, 31 minutes. So I'll page down like that and carry on, page down, page down, page down until I come to 30 degree, 50 minutes. And there you see 30 degrees, 50 minutes. And there'll be now for each of the stormwater duration events, whether it's 2 minute, 5 minute, 10 minute, 20 minutes, like that. Right. So you're going to do like that. So you're going to page across for that. Now we're looking for a 22 and sorry, a 1 in 5 year storm. So this column G, if you, let me go up again. That's the return period. You can see the RP I spoke about. Make a note of that. Right. So the RP is for uh, it's come down again now. That's why I highlighted in yellow. So we're looking at the 1 in 5 year return period. So we now have that 1 in 5 year return period, and we got the correct latitude and longitude. We now need to find the duration, the storm, the event that we want over here. Right. So again, note. Let's go up to the columns there. You can see that we have a 15-minute event and a 30-minute event. So ours is 22 and a half. So we will then have to interpolate between those two values. So to come down here, when we come to this point here, you can see I've highlighted in yellow for it, so it's easy to follow. You'll have to now interpolate between this 29.8 and 38.9. Right. Let me just see if I can enlarge the view. Uh, just 150. That might be a bit bigger. You may not be able to read those values, so I just enlarge the screen. Right. So between the what was it? Those two values, we will now have to interpolate between the 29.8 and the 38.9, between the 15-minute and the 30-minute event. The 29.8 is for a 15-minute event, and the 38.9 is for the 30-minute event. We're looking at 22.5, so we will then get an interpolated value, and that will give us the millimeter part in our intensity calculations. So that's the point rainfall that we need. So this is where you come and you look up the site-specific data that eThekwini has provided for you. So they have the spreadsheet. It covers the entire eThekwini region. And for any point in eThekwini, you can get the rainfall data, the point rainfall data. And this is based on historical records. Right? They have historical records, and it's been derived from the historical records. They do have points in the city where they measure the rainfall, various areas and various points, and it's derived from that. So this is from historical data. And so interpolate between those two values. And so let me go back and just bear with me. I'm going to have to unshare the screen. Any queries regarding this before I unshare it? Do you have any query regarding the spreadsheet? Anyone? No query? Okay. I assume you now know what to do for how to measure, how to use these spreadsheets, right? The spreadsheet is on Moodle, so you can download it and utilize it from there. Okay, let me go back and unshare, and I need to go back to that calculation there. Where were we? The design manual, yes. Okay, so that's how that interpolation was done, and that's how they've come up to this value and you can see the interpolation it's being done, the TC, so that's the 15-minute and the 30-minute. You don't need to by heart this formula. You're in third year, you should know how to do those interpolations, right? They're saying for intensity for 15-minute, the rainfall for 30 minutes, that whatever value you read off from those tables, and then you would add it to all that value there. In third year, you'll know how to do an interpolation and you can work it out. And that's how that value is there. I just want to show you, I have worked it out. So if you want to know what those values were, just bear with me. Uh, uh, okay, I've worked it out using MathCAD. All of this, these calculations are repeated here. And you'll see that you might find it easier to follow these calculations. So I will put them up for you on Moodle. I just want to show you that this to show you the interpolation was done. You can see if you look at this rainfall intensity. Okay, the concentration time was 22.555. That's MathCAD has rounded up, and now for the point rainfall or to do that calculation to do the interpolation, you can see that. There's the 29.8 and the 38.9 that you can see, and we interpolating it for 22.555, that value, the TC value. Okay, let me just get my pen. The TC here, you can see is 22.5 minutes, and that's what we're interpolating it for that value, right? We got the 15 and 30, and that's how we're doing the interpolation. And you can see those were the two values that I read off from that table. Right? Just now when I showed you that spreadsheet, you saw those two values there, 29.8 and 38.9. So that's where those two values came from that spreadsheet. And you can then work it out and you then arrive at a rainfall intensity of 98.349, which is they just given you that value at this point of view. So I know many students get confused with that, so that's why I've spent some time explaining to you how this value was arrived at. It's not a thumb suck figure, right? It's a derived value for that 98.9. Now that you have that intensity, we now have all the variables for our uh, rational formula, and we will then substitute. You can see that the return factor 0.55, that 99, that's the intensity that's been plugged in over there, and that's the 2 hectares. Right, the area that's been substituted, and this is the 0.5 here. That was the C value that we worked out here, the coefficient, right? And it's called C1 because it's the coefficient for area one, the catchment one, and you can see the final value equal to 0.5. And that's where all those values have come. You now end up with a value of 0.151 cubic meter. QMEC stands for cubic meters per second. So it's just cubic meter per second. That's what one QMEC is. That's how we normally, instead of saying meter cube per second, the common terminology is to say QMECs. Like that. Right, so we now have the Q that's going to arrive at that particular point A, at point, the rain or the intensity, the flow at point A. We then want to go on and proceed and design the pipeline uh, for from A to B. Right now, between A and B, there is no further input in the pipeline. It's just whatever has arrived at point A goes into the pipe, and that's what's flowing in that pipeline AB. Right. Uh, for catchment area 2, it only enters the system at point B. So there's no other flow entering the flow in that pipeline AB. So we can then go ahead and design this pipeline AB. And now the design is very similar to what you've done for sewer reticulation, right? To do that particular design. Uh, to determine that, you can use your Manning equation, and you can see the Manning equation is given over here. You've got the Manning equation, and you would then you also need the slope of the pipeline between those 2 points. You determine that. So you can again you more or less follow the ground profile to get that slope, but you can adjust it if need be. If you want to make it slightly steeper slope, you can do that. This means the pipe will get more deeper. But from based on the ground level, so that's the slope that was derived from there, and that's substituted into this equation, and you can then determine. Uh, you have to also select a suitable pipe size and the Manning coefficient. The minimum pipe diameter for stormwater is 300 millimeter. Very different from sewer reticulation where it was 150. Right, so here it's 300, the minimum. Uh, and again, it depends whether you're in a road servitude or whether you within a property. You're not within the road servitude, so that's why it's 300. If you're within the road servitude, it would have been uh, 350 millimeter. The Manning coefficient you can see for 0.013 for an older pipe. When the concrete pipe is new, it's 0.011, but we'll use it. The pipe will age with time, so we'll use the value of 0.013 at that point over there. Right, so for that 300 millimeter diameter pipe, that's your trial size. You got the slope and you got the Manning coefficient. You can then proceed like what you've done in sewer reticulation and check that. Now, and you'll find out that the capacity of that pipe is 180 or zero point 0.18 cubic meters per second, but we have a flow of 0.151, so our flow is less than that, so the 300 diameter pipe would be adequate. The next part of the calculation that you see, this is for culvert design. Now, you would have done culverts with Dr. Siam, or you may have done it in your road design also with Ronnie Govender, or both of them. You would have covered culvert design over there. But in this module, we do not cover culvert design. Uh, Now, what happens in a culvert? Why do you need to do these checks for culvert design? When you have a culvert, the flow is either controlled. You have what we refer to as inlet control or outlet control conditions. And so that is briefly explain it to you. For example, if that's your pipeline like that, and you got, for example, uh, mm, sorry, I'm not drawing that right over there. Uh, you may have a road or something like that, and you have the culvert flowing through like that, and you have something like that. And that's your road, whatever. And you got the culvert pipe over here, and you'll have an outlet point there, and you'll have an inlet point on the left hand side like that. Right now. Uh, Though you get a certain amount of loss because the flow has to enter into the pipe at that point over there, and you also get a certain amount of loss at the outlet over there as the water is released over there, depending on the shape of those walls that you have at those points over there. That the wing walls of those culvert depends on how the angle of those wing walls and things like that. The various factors that affect it. So the pipe may not necessarily run full. There might be a restriction in how much water can enter the culvert at this point. But then the slope is quite fast, and then you'll get. So you might get, for example, initially the pipe is sort of like full over there, and then the flow is like that in the pipe, like that, running like that over there. So you have a certain depth of flow like that, and then it outlets at this point of it. This is inlet control. So as you can see, the inlet is what's throttling the flow. Right. You won't necessarily get a nice full pipe that's flowing like that when you've got inlet control. Or when you get outlet control, the pipe is full over here, but you cannot get the full flow that you actually desire because it's being slowed down. The amount of flow that can exit over here, the slope of the pipe would allow a larger flow, but the outlet conditions are such that they're slowing out, they're holding back the flow a bit, and then we have what we call an outlet control on this pipe over here. So it becomes quite complex. You would need expertise to design a culvert for that, and I'm sure you would do cover that with Dr. Siam in your hydrology course for that over here. They make mention of it over here just to show you that it's not really going to be a factor in this particular design because to get that particular flow of 1.187 cubic meter through a culvert pipe, right? So not when you worked out this Manning value here, and you got this 0.18 value, this is for a continuous pipe at that slope. Right? So you got a continuous pipe. You don't have this a short length of pipe. You're talking of a continuous pipe. So you don't have these inlet and outlet conditions that are controlling the design of flow in the pipe. Whereas for a culvert, it's a pipe of limited length. So it's usually maybe either 20 meters or 30 meters in length. And it's the inlet and the outlet conditions that control the flow. So it's not strictly the flow is not happening strictly according to the Manning equation, what the Manning equation would predict, because these would control that. So to get that same capacity of point, what was it, 0.151, to get that flow over there, what it requires, they call it backwater. Right, so it means that you got this road embankment, and you would require, for example, from the invert of the pipe, the water to dam up to a level of zero point 0.1 of zero point 0.7 meters, right, from the invert of the pipe. So you'd need 0.7 meters of the water level would be there. So you got a little bit of water backing up in the culvert over there, and then you would achieve that flow of 0.157 through this, where you have with inlet control conditions. Right. And what they're saying here is that zero point 0.7 the pipe would already be uh, deeper than that in the ground. The cover requirement for it would be at least zero point 0.7. So it's not going to it's not going to control the design. The fact that you would need the road to be at a certain level or this pipe invert level to be dropped so you can achieve that level of 0.7 meter depth over there. It's easily achievable. It's going to be achieved no matter what. That's what this, you may be wondering what's all this discussion about over here. So that's what it's all about. But just bear in mind, this is not the sum of it all when it comes to culvert design. It gets complex, and you'll cover it in your in your hydraulics modules. You should have done culvert design over there. So I'm just going to leave it over here. They just mention it in as a by the way, this as a comment here to tell you that they've considered it, and it's not a consideration. Right? The backwater level for that it will easily be achieved, and you will attain that value of 1.157 meter cube per second through that particular pipe. And so that's what decides this final design on this pipe. The velocity, 2.5 meters per second. That's adequate for stormwater. So you know it's going to drain out quite easily. Uh, The flow length in that pipeline that's measured here, that's 80 meters long. So that from A to B, with your scale rule or something, you would have a scale for this map, and that would be measured. And that's where the length of it has come. That's where that's mentioned, the 80 meters. And the velocity, that's those checks are done. And this is basically all summarized in this, the concentration time. Oh, sorry, wait, I missed something here. I haven't explained this well. Let me just repeat this to you. What's happening here in this calculation, and they're important again, this part of here. Let me just delete the clutter. Uh, so I just want to explain it to you. Yeah, okay, and then I'll end the lecture. In the next lecture, I'll continue with uh, the inlet B, and we'll look at that design further down for the rest part of it. Today's lecture, I'll end with the discussion on this. Now, observe in this, we measure the concentration time of at point for the arrival at point A. We said that that was 22.5 minutes, right? That was the time of concentration at that point over there. Then the flow enters into the pipe. It has a certain, we need to know the velocity of flow in that pipe, right? Because once we know the velocity of flow in that pipe, it'll take us finite time for the water to flow from A to B. Right? So the concentration time at B is not 22.5 minutes. It's you have to add, if you know the velocity and you know the length of it, you can then work out the time it takes for the water to flow from A to B. And that will give you the concentration time for B at point B. Right? For if you point B is your area of consideration, then you would then need the concentration time at point B. And you need that time because to design the pipeline from B to C1 or from B to C2, yeah, you see the B to C2, you need that concentration time. Right. So to get that concentration, to design that pipe from B to C2, you would need the concentration time at B. So it will be the concentration time at A plus the time it takes for the stormwater to flow from A to B in that pipeline AB. So that's what's being done in this last bit of calculation. How long does it take for the water to flow from point A to point B in the pipeline? We worked out that the full bore velocity would be that 2.5 meters per second. If you want it to be more accurate, it would be to work out with the actual flow conditions instead of full bore velocity, to work out the actual velocity. And you do know how to do that from your sewer calculations. And you then work out how long it takes to that. And that's how you can see it's worked out over here at zero point 0.5 minutes or 30 seconds. And that's how the value of 23 minutes is arrived for the time of concentration at point B. Right. Uh, so that's for that particular that particular point over there. In my calculations, I've done it. You'll see just to show you the calculations that I've done. I just want to clear out the clutter there. Uh, once we've decided on this once we have that flow, the 0.151 or 157 liters per second, whatever, that you've got that intensity that we've worked that out. This is now for similar to what you've done in your sewer calculations. You converted it to liters per minute. You're familiar with this chart, this nomograph. You can use this nomograph to get an idea of what pipe would be adequate. You can use that. You can then also check the flows using the same thing, exactly what you used in sewer design. You can then use this table here also, and you would then come up and you can confirm. You can then go ahead to design that pipeline AB. And that's what you see in my calculations I've got here. I'm showing you from the nomograph what we've done here, all those similar to what you've done in the sewer calculation. The slope, we're assuming a pipe diameter of 300. I'm working here with the 0.011. That's for the new pipe. And then the full bore. Okay, now in stormwater, it's with the stormwater design pipe. Remember, the pipe dries out, right? When in between events, the whole of most of winter, there's no rain, the pipe will be dry. So you're not going to get that same uh, what they call it, like not scum, but that slime buildup on the pipe, like what you get on a sewer pipe. A sewer pipe flows every day. It's wet every continuously, right? So you get a slime buildup. On a stormwater, it can still look like new 10 years down the line. It can still, the inside surface might still be like new. So that's why I've assumed a value of 0.011 for a new concrete pipe. And then you can check the full bore velocity. You can see the full bore velocity I've worked out. And then the actual velocity calculations you can do. You're familiar with these calculations. You've done them for sewer reticulation, the actual depth of flow. I've done that. Now, when you do the actual velocity, once you've got the actual velocity, you can then work out, and you know the length of the pipe, you can then work out how long it takes for the pipe, for the water to flow. Right. So the actual velocity times the length of the pipe, that from that calculation, you can see that's the actual time it will take for the water to flow from point A to point B. That 35 seconds, they said half a minute. So that's what you get. And that's how the final concentration time I arrived at of 23.128 minutes further. Okay, so this is just the first pipeline. I see the time is at 11:57. I know you have a lecture after this. So I'll continue with this discussion in Wednesday's lecture. We'll then go ahead and consider the remaining portions. Just before I end this lecture, just to come back to the sketch, something just caught my mind now that I would like to just mention to you. Where am I? Sorry, just bear with me. Let's find the Ethiopian map here. Uh, so we've considered, we've done the pipeline from A to B. In the Wednesday's lecture, we'll then design the pipeline B to C2. And to do that, we then have area 2. We'll have to determine the flow from area 2. And then there's a pipeline from B1 to B also that flows into that catchment. So we'll have to look at that particular pipe and the flow for that. And then we look at from B to C2 like that. Now, you might be wondering, but what's the C1 and C3 there? Right. Just remember, I told you this is a critical point, right? It's a low point, it's a critical point. So that's all. Those are this additional catch puts provided to ensure that the flow does get into the pipeline and you don't get ponding or you don't get uh, water flooding behind here to enter that particular catch put like that. And so it's to ensure that you get proper drainage. So the pipeline is actually from B, the design will be from B to C, and we just assume that all the flow enters through C2, but actually C1 and C3 do actually assist in getting that flow into the pipeline, and they're just there as if one blocks up, then the other one is still there, and the water will flow through the other one. So because it's a critical point, it's a low point in the system, so these are like backup catch puts that are provided over here in this particular drawing that you see here. Any questions? Anybody? Any questions with regard to what we've covered today? Hopefully, you now get the gist of it. After this, it's going to follow a similar pattern to what I've explained today. Today was the most important one to get you to understand where all these numbers and are coming from. Hopefully, you now have enough information and you can follow those designs. Okay, if there's no further query, I'll end the lecture at this point. Let me just stop the recording.